The directionality of a chemical reaction means whether it will occur or not. Whether a reaction occurs or not depends partly on the stability of the products compared to the stability of the reactants, which is related to how much heat is released or absorbed during a reaction. When heat is released during a chemical reaction, the products have more stable bonds or lower potential energy than the reactants. When heat is absorbed during a chemical reaction, the products have less stable bonds than the reactants or have higher potential energy than the reactants. One way to quantify the stability or potential energy of bonds is the bond dissociation energy, or capital B, capital D, capital E. Bond dissociation energy is the energy required to break 1 mole of a given bond. Bond dissociation energy values are averages based on experimentally determined values. The greater the bond dissociation energy, or the more energy required to break a bond, the more stable the bond is. The more stable a bond, the less reactive it is. Another way to think about the bond dissociation energy is that it is also the energy released when a bond forms. The more energy that is released when a bond forms, the more stable that bond is. Table 7.1 has a listing of average bond dissociation energies in both kilocalories per mole and kilojoules per mole. Looking at this table, which bond is the most stable? Pause the video to figure this out. Since the triple bond between two nitrogen atoms has the highest bond dissociation energy at 226 kilocalories or 946 kilojoules per mole, it is the most stable. This is the energy that would be released when the bond is formed, or the energy required to break this bond. We have evidence for the stability of this bond in our everyday life. The nitrogen in our atmosphere is triply bonded, and it is very non-reactive.